left hand side, and we differentiate the right hand side. G prime of x is 1 over x cubed plus 1. Now let's discuss a couple of things here. Here's number one. What happens if this is not x? I'm just going to change the problem a little bit. Let's say this time is the integral from 1 to x cubed from 1 over t cubed plus 1 dt. I'm sorry? Yes, Vanessa, you want to say something? Careful. So I'm changing the problem. I just create a new problem right now. So when I differentiate a function, if it has another function in it, what do? I differentiate the inner function. Here, there was no need to write x prime. Why I did not need to differentiate that? Because it's 1. Stay with me. Great job. Okay, so then, now when I differentiate both sides, the left-hand side is g prime of x. The right-hand side is 1 over x cubed to the third plus 1. But now, because I put in t, x cubed, 3x squared. That's one thing that I needed to mention. And we'll have examples in a second. Yes, please.
How did we get 1 over x cubed to the third?
It's 1 over t cubed plus 1, and I replaced t by x cubed.
Okay.
So then the final form will be 3x squared over x to the 9th plus 1. So that's one important item. Here's the second important item. You notice that g of x is always from a number, but we don't really care what this number is. It doesn't come into play at all. Okay, from f of t dt. But what if I'm given g of x as the integral from x to 3 from f of t dt? How will I find the derivative of this function? The answer is not yet. It's not presented in the correct form. The correct form is the number as the lower limit and the function, or x if you want, as the upper limit. But what do we just looked at? And I've added a property today. If I swap the limits of integration, what happens? It's negative. So the function is negative the integral from 3 to x from f of t dt. Now this is ready. I can differentiate it. And what will I get? The minus has to stay. And what do I get? That's it. That's it. G prime, of course, G prime. G prime. So we're going to apply these in more complicated situations right now. Let's say, before we look at more complicated situation, let's look at 16 and 18.
So why
yes?
Does it become negative again?
So the function has to be given with a number as the lower limit and whatever as the upper limit. This example that I showed you, it had them reversed. So the property of the definite integral is that the integral from a to b is negative the integral from b to a. We had to reverse that first before differentiating. Better? Perfect. So 16, h of x equals the integral from 1 to the square root of x from z squared over z to the 4th plus 1 dz. Remember, when the limits of integration are functions, either one or both, we will never be asked to determine the integral. No. We are only asked to find the derivative of this function given in a form of an integral. So, since the limits of integration are in the normal position, the lower one is a number, the upper one is whatever with x in it, then I'm ready to
That's number 14.
Is it? Thank you. Thank you. My apologies. So we're going to still look at 16 and 18 in a minute. So then, what do I write? So the square root of x squared, which is x, the square root of x to the fourth, which is excellent, plus 1, times, that's it. And this is done. Excellent, well done. This one is z because when I differentiate the square of x, I get 1 over, there is no more z here. All z's are gone because we differentiated. Yes, when I differentiate the square root of x, I get 1 over 2 the square root of x. Is that better? 2. Very good. Finally, 16.
So we're just plugging in the upper and lower limits.
We're not plugging in the lower limit. We are not determining the integral. We are differentiating this integral. Better? 16.
By plugging in the upper limit?
So because g of x, the integral from a to x from f of t dt, when we differentiate both sides, that's exactly what we do. We get g prime of x to be f of x. Better? Yeah, we have to review this. We have to talk about it several times. Once, 1 or 2 or even 5 problems may not be enough. So finally 16, y equals the integral from 0, I see x to the fourth. Is it x to the fourth? Cosine squared theta times, or d theta, cosine squared theta d theta. No one is asking us to evaluate anything. This is a function. If one of the limits is a function or depends on x, in other words, we are only asked to find y prime. Can anyone dictate y prime? That's it. That's it. Okay, I think we should do one more. We'll also look at 18. Any questions for me? Okay, y equals the integral from sine x to 1 from the square root of 1 plus, I think it's t squared, is it? Yes, dt. Now I observe something that tells us that this is not ready for differentiation yet. Yes, Ricky? Yes. So I will have to write that this equals to what? Exactly. The integral from 1 to sine x, the square root of 1 plus t squared dt. Now I can differentiate the beginning and I can differentiate the end. So then y prime, and dictate when you're ready. I have to copy the minus.
Negative.
Yes?
1
plus sine squared x times
2x. The sine squared x.
So when I differentiate, all that happens is this goes away and this goes away. Nothing changes here. T is replaced by sine, but since this is not plain x, then I have to multiply by cosine x. Like we did here. Here we multiplied by 4x to the third because this upper limit was not plain x. When the upper limit is not plain x, we have to multiply by the inner function prime.
Is it not 1 over?
When I differentiate sine, I get cosine. I'm not differentiating the square root. When I differentiate an integral, all that changes is this goes away and this goes away. Nothing changes here other than plugging in t sine. And then I have to multiply by the derivative of sine. Is this okay? Yes, everyone? Okay, so let's look at one more. Please choose if you'd like 55 through 59. These are slightly more difficult. 55 through 59, page 395. Okay, 58. 58 we have, this time this one is denoted by uppercase F, the integral from the square root of x to 2x from arctangent t dt. And now I'm sure you notice that two discrepancies. Number one, the lower limit is not a number. This is fine, but I have a problem with this. Let's refresh our memory on one of the properties. We said that the integral from a to b from f of x dx is the same with a sum of two integrals. Let's say I have a number between a and b. Give me a letter. C. So C is a number between a and b. So then how do I write the sum of the integrals? A to c and? Very good. So this is from f of x dx and from f of x dx. I can break the interval into 2 pieces or 10 pieces if I want to, but I only need 2. But now you can say, where will you break this interval? Where do you know where it is, first of all? How would you break the square root of x, comma 2x? Where will you break it? Oh, here's how am I going to break it into? So then the integral from the square root of x to 2x from arc tangent t dt is the integral from the square root of x to whatever you want. I don't care. Plus from the same number to 2x arc tangent t dt. If you want to put 0, put 0. If you want to put 5, put 5. If you want to put 1500, put 1500. It doesn't matter. It's not going to come into play anyway. Now I'll say the second integral is ready for differentiation, but the first one is not. What do I do to it to make it ready? Exactly. Negative the integral from whatever you want to the square root of x arc tangent t dt plus the integral from that number to 2x arc tangent t dt. And now I'm ready to differentiate f prime. Please differentiate this, and please differentiate this, and give me the answer. When we differentiate the first one, what do we get? Negative has to stay up front.
Negative 1 over
Arc tangent, we are not differentiating the function. We get the function, pure function itself. Arc tangent of the square root of x times the inner function prime, which is 1 over 2 the square root of x plus very good 2x, I have to put the argument in, multiplied by exactly the derivative of 2x. That's it. This is it. Let's work on another. Please choose. Yes. Sure. Any questions on this, please? Any questions? Any questions? We are differentiating an integral, not the function inside. And when we differentiate an integral, we get the function with no changes. Let's look at 59. Now I hope you're going to walk me through 59. The integral from cosine to sine. So y equals the integral from cosine to sine x from natural log 1 plus 2v dv. Is this integral ready for differentiation? No. So what should we do first?
Split it into some.
Good. So can I already write the integral? So it should have been from cosine to the number. So I'll write it from the number to cosine with minus in front. And plus.
The integral from number.
Exactly. To sine x natural log of 1 plus 2v dv. Awesome. And now we are ready for y prime. When you are.
Natural log of x cosine x. No.
1 plus
2
cosine x. Excellent. Times.
natural log of
Negative sine x. Differentiate cosine. Plus.
natural log
Yes. 1 plus.
2 sine x
Very good. Times the inner function prime.
cosine.
That's it. You don't have to do anything. I will just remove these negatives because they're multiplied. So then the answer will be sine x natural log 1 plus 2 cosine x plus cosine x natural log 1 plus 2 sine x. Any questions? Of course, I didn't mention, but it's clear. So let me show you where the fundamental theorem of calculus part 1 is. Of course, the function must be continuous. There is no discussion there. We know that. Then the function g defined by this integral is continuous and differentiable. And g prime equals f of x. Okay, so that's what we just did. See, I just want you to see where it is. And we can look at one more property on page 384. And there is nothing else that we need to look at. I'm just looking to see if I forgot anything. Nope. I didn't forget anything. We covered everything. But I like to look at a property which we did not look at yet. Use the properties of integrals. Use the properties of integrals, page 384, to verify the inequality without evaluating the integrals. So 56 caught my eye. 57, I don't know why it's in red. We can look at 57. You want to do 57?
I like 57.
7?
Yeah.
Very good. So let's do 57. So here we're only asked to use the properties of the definite integral, not calculate the integral. So here it is, 57 on page 384, and they're asking us to show that this is true. This is 5.2, the properties that we started with last time, and I didn't show you any example. Okay. We cannot, by the way, don't even attempt to determine this exactly. You can't. I can't. We can't. Why? Because we don't know the antiderivative of the square root of 1 plus x squared. Don't even try. Okay. Ready? Well, where is my starting point? Well, my starting point is right here. What does this say? That x is between, right, that's very clear. Good. If a number is between -1 and 1, can anyone tell us which type of number, or can you say anything about x squared? And you should ask, how did you come up with this? Well, I peeked here. So there is an x squared. I know that x is between -1 and 1. So remember the graph of x squared between -1 and 1, right? Between -1, let me graph it. So this is the graph, -1, 1, 1, 1. So this is the graph of x squared. So for x between -1 and 1, what are the possible values of this function? From 0 to 1. Do you agree with that? For any number between -1 and 1, x squared cannot be a number other than between 0 and 1. There is nothing else. If you square 1/2, you will get a number between 0 and 1. Yes?
What if we did reducing the symmetric?
Yes.
Would that be in this case?
No, we're not integrating. We are trying to build this integral with two sides. But it's a very good question. Yes. Do you agree that if you have in your pocket any number between -1 and 1, and you square that number, the result cannot exceed 1 and it will not be less than 0?
Yes.
If it's -1/4, if you square it, it's between 0 and 1. If you have 1/16, if you square it, it's going to be between 0 and 1. If you have -1 and you square it, it's going to be between 0 and 1. If you have 1 and you square it, it's between 0 and 1. Do we agree? Okay, so far, stay with me. We built this piece. What should I do now to all three sides to continue building that function? Ricky?
+1.
Exactly. I haven't gotten there. I don't have the 1. So I will have to add 1 to all three sides. 1 less than or equal to 1 plus x squared less than or equal to 2. Do we agree with this? If I established that x squared is between 0 and 1, I'm allowed to add 1 to all three sides. And the inequality will not change. Good. Since these three are all positive numbers, do we agree? This is a positive number, this is a positive number, this is a positive number. Then if I take the square root from all three, this will still be correct. So now I'm using the property that we had looked at last time. So now I'm integrating. Can anyone give us the integral on the left? Of course, between -1 and 1. -1 and 1, -1 and 1, -1 and 1. So let me write this one more time because it looks confusing. -1 to 1 from dx, because it's just 1. The square root of 1 is 1. Less than or equal to -1 to 1, the square root of 1 plus x squared dx. Less than or equal to, this is the square root of 2. I can put it in front, dx from -1 to 1. How much is this? You can say, I can calculate it. Yes, we can. So what function prime is 1?
X.
Very good. From -1 to 1. What function prime is 1? Good. Square root of 2x from -1 to 1. Perfect. And now I can determine the left, and I can determine the right, and I'm done. Just need more paper. So x, I plug in, I don't need to write it one more time. So I plug in 1. What do I get when I plug in 1? Well, the answer is 1. But then when I plug in -1, remember the fundamental theorem of calculus, part 2, I subtract. I plug in 1, and then I subtract when I plug in -1. same thing here. The square root of 2, I plug in 1 minus plus 1. The left-hand side is 2. The middle is the square root, the integral from the square root of 1 plus x squared dx. And the right-hand side is 2, the square root of 2. And that's exactly what they wanted us to show. Any questions? Yes.
The last part, like your final answer, you have 2 square root 2 at the end. How did you get that?
So when I plug in 1, and then when I plug in -1, I have to subtract.
Okay.
Uppercase f of b minus uppercase f of a. So this will be the square root of 2, 1 minus -1.
Okay.
Yes, Braden?
So we don't have to say what function prime is.
No,
square
you
root of
can't.
1 plus x squared.
We can't. So the problem was only asking us, let's read it one more time. Very good question. The problem was saying this. Use the properties of integrals, of course, definite integrals, to verify the inequality without evaluating the integrals. So without evaluating these, and this. And that's all we needed to show. We started by building the inside function. So I started with x between -1 and 1, I squared, I got this. I saw that I needed x squared, but I also needed the 1, so I added 1 to all 3 sides. I got an expression on the left, just a number. The square root in the front, in the middle, because all of those are positive, so I can take the square root. So I'm hinting towards this property, because I determine this number and I determine this number, and then I integrate each piece. And when I integrate the left, I get 2. When I integrate the right, I get 2 to the square root of 2. And when I integrate the middle is what I need to show. So all we were asked to determine or show is that this integral is a number between 2 and 2 to the square root of 2. We don't care what it is. We only wanted to show that this integral is a number between 2 and 2 to the square root of 2. Better?
Yeah.
Very good. Okay, so we have 10 minutes left. What would you like me to do? Would you like to go back to this test 4? Let me just say one more time